Determining the correct wire size for an AC condenser motor involves several factors, primarily related to the motor's operational characteristics and adherence to electrical codes, such as the National Electrical Code. The key parameters you need to consider include the motor's rated load amps, or RLA, the minimum circuit ampacity, often abbreviated as MCA, and the maximum overcurrent protection, or MOP, which essentially sets the limits for the breaker size. The RLA represents the steady-state current the motor draws when operating at its rated load. The MCA is the minimum ampacity the circuit conductors must have to safely supply the motor, taking into account factors like continuous operation and potential harmonic currents. The MOP sets the upper limit for the circuit breaker or fuses, protecting the motor and circuit conductors from overcurrent conditions. The National Electrical Code Article 430 provides detailed guidelines for motor circuit sizing and protection. You must follow these guidelines to ensure safe and code-compliant installations. Firstly, determine the motor's rated load amps, or RLA, from the motor's nameplate. This value is crucial for calculating both the minimum conductor ampacity and the overcurrent protection requirements. Secondly, calculate the minimum circuit ampacity, or MCA. The MCA is typically calculated by multiplying the RLA by a factor, usually 1.25, to account for the motor's continuous operation. This means MCA equals 1.25 times RLA. For example, if a motor has an RLA of 11.9 amps, the MCA would be 1.25 multiplied by 11.9 amps, which equals 14.875 amps. Thirdly, determine the maximum overcurrent protection, or MOP. The MOP is the maximum size of the circuit breaker or fuses allowed to protect the motor circuit. The NEC provides tables and guidelines for determining the MOP based on the motor's type, horsepower, and voltage. It's essential to consult these tables in Article 430 to ensure compliance. Typically, the MOP is selected based on a percentage of the RLA, and this percentage varies depending on the type of motor and the type of overcurrent protection device. Fourthly, select the appropriate wire size based on the calculated MCA and the ampacity ratings of conductors as specified in NEC Table 310.15b16. The wire must have an ampacity equal to or greater than the MCA. For example, if the MCA is 14.875 amps, you would need to select a wire size with an ampacity of at least 14.875 amps. Common wire types like THHN, THWN, or XHHW have different ampacity ratings depending on their size and insulation temperature rating. Remember to consider the terminal temperature ratings of the equipment, typically 60 degrees Celsius or 75 degrees Celsius, and select the wire size based on the corresponding ampacity ratings. Fifthly, verify that the selected wire size is also adequate for the MOP. While the MOP sets the upper limit for the breaker size, the wire must still be able to safely carry the current allowed by the breaker. If the breaker trips, the wire will be subjected to that current until the breaker interrupts the circuit. So, the wire's ampacity must be sufficient for the MOP. Sixthly, consider voltage drop. Voltage drop occurs when the voltage at the motor terminals is lower than the supply voltage due to the impedance of the circuit conductors. Excessive voltage drop can cause the motor to overheat, reduce its performance, and shorten its lifespan. The NEC recommends limiting voltage drop to a maximum of 5% for motor circuits. To minimize voltage drop, you may need to increase the wire size, especially for long circuit runs. Use voltage drop calculators or consult engineering tables to determine the appropriate wire size for the specific circuit length and load. Seventhly, ensure proper grounding. Grounding is crucial for electrical safety. The equipment grounding conductor, or EC, provides a low impedance path for fault current to return to the source, allowing the overcurrent protection device to trip and clear the fault. The size of the EGC must be determined based on the size of the circuit conductors, as specified in NEC Table 250.122. Make sure to use the correct type and size of grounding conductor and properly connect it to the motor, equipment, and grounding system. Eighthly, follow all applicable codes and standards. Electrical installations must comply with all applicable codes and standards, including the NEC local built-in codes, and any specific requirements from the authority having jurisdiction. Failure to comply with these codes can result in fines, penalties, and potentially unsafe conditions. Always consult with a qualified electrician or electrical engineer to ensure that the installation meets all requirements. 9. Consider derating factors. In certain situations, the ampacity of conductors may need to be derated, which means reducing their allowable current carrying capacity. Derating factors may apply when conductors are installed in raceways with multiple conductors, in high ambient temperature environments, or at high altitudes. The NEC provides tables and guidelines for derating conductors in these situations. Failure to apply derating factors can cause the conductors to overheat and potentially fail, leading to a fire or other hazards. 10. Document all calculations and selections. Keep a record of all calculations, wire size selections, breaker sizes, and other relevant information. This documentation can be helpful for future reference, troubleshooting, and inspections. It also demonstrates that the installation was designed and installed in accordance with applicable codes and standards. For the specific scenario you provided, the maximum breaker requirement is 25 amps, the minimum breaker is 20 amps, the RLA is 11.9 amps, and the minimum supply ampacity is 16 amps. To determine the appropriate wire size, we'll follow the steps outlined above. First, the RLA is given as 11.9 amps. Second, the minimum circuit ampacity (MACR) is calculated as 1.25 times 11.9 amps, which equals 14.875 amps. Third, the maximum overcurrent protection (MOP) is specified as a maximum of 25 amps and a minimum of 20 amps. This means the breaker size must be between 20 amps and 25 amps. Fourth, select the wire size based on the MCA of 14.875 amps and the MOP of 25 amps. According to NEC Table 310.15b16, for copper conductors with THHN insulation at a 75 degrees Celsius terminal temperature rating of 14, American wire gauge or wire has an ampacity of 20 amps, and a 12 AWG wire has an ampacity of 25 amps. Since the MCA is 14.875 amps, 14 AWG wire would be sufficient based on ampacity alone. However, the MOP is 25 amps, and the wire must be able to handle that current until the breaker trips. A 14 AWG wire with an ampacity of 20 amps would not be adequate for a 25 amp breaker. Therefore, a 12 AWG wire with an ampacity of 25 amps is required to handle the 25 amp breaker. Fifth, check for voltage drop. For a typical residential or commercial installation, voltage drop is usually not a significant concern for short circuit runs. However, if the circuit run is long, it's essential to calculate the voltage drop to ensure it's within acceptable limits. If the voltage drop exceeds 5%, you may need to increase the wire size to minimize voltage drop. Sixth, ensure proper grounding. The size of the equipment grounding conductor, or EG, must be determined based on the size of the circuit conductors. According to NEC Table 250.122, for 12 AWG conductors, the EGC must be at least 12 AWG copper. Seventh, follow all applicable codes and standards. Ensure that the installation complies with the NEC and any local built-in codes. Consult with a qualified electrician or electrical engineer if you have any questions or concerns. In summary, based on the given parameters, a 12 AWG wire is required for the AC condenser motor circuit. This wire size meets the minimum ampacity requirements of 16 amps, is adequate for the MCA of 14.875 amps, and can handle the maximum overcurrent protection of 25 amps.